Antennas, an introduction series on antennas and wave propagation, lecture number 1.10. Antennas are mostly linear. Antennas are mostly passive. Antennas are also mostly critical because they they decide the performance of the wireless communication system in which they are used. In the present session, the focus is on terminology, physics, and also the functioning of antennas, not only as radiators but also as probes. Here in this session, we also consider the role and importance of antennas in the functioning of wireless communication systems. To begin with, we consider a wireless communication system. Wireless systems cannot be designed without antennas. To understand antennas, therefore, it is apt, it is appropriate to consider a wireless communication system. A simple block diagram of a wireless communication system is shown. On one side, we have a transmitter, on the other side, receiver. This entire system is there in place to transfer information from the location of transmitter to the location of receiver. Usually transmitter and receiver, these are separated by large distances. The transmitter output is fed to an antenna through a coaxial line. The antenna that is there on the transmitter side, it is called transmitting antenna. This transmitting antenna then pumps out the signal that is fed to it, and mainly it directs the signal towards receiving antenna, receiver side. The signal that was emitted by transmitting antenna, it travels in different directions, and it all depends upon the directive nature of the transmitting antenna. Most of this signal then travels towards the receiving antenna. This journey is through free space or atmosphere. The distance between transmitting and receiving antennas, it may be tens of kilometers, it can be even hundreds of kilometers. Receiving antenna, which is connected to the receiver circuit, it collects a part of the signal that has been emitted by the transmitting antenna, and it then hands it over to the receiver through a coaxial line. The receiver then processes the RF signal and gets back the original baseband signal that has been the input to the transmitter here. So receiver output is the signal that has been given at the input terminals of the transmitter. Now, the importance right now is regarding antennas. We can see one antenna on the transmitting side, another antenna on the receiving side. So antenna occupies two places in a wireless communication system. With this understanding regarding a wireless communication system and the importance of antennas in that system, let us move further to explore the world of antennas. Here is a brief regarding what has been illustrated in the previous slide. Transmission line is usually a coaxial line. Coaxial line is selected because of its mechanical flexibility and no radiation losses. What is this transmission line? It is the line which connects transmitter circuit to the transmitting antenna. It is also the line that connects receiving antenna's output to the receiver circuit. Usually, coaxial lines are used. Waveguides also can be used, but they are stiff and also their size becomes large at lower frequencies. Coaxial line is the appropriate one, and hence, usually it is the coaxial line that is used. Antennas appear at two places in the link we have already seen, once with the transmitter and once with receiver. Transmitting antenna is supposed to push all the signal power towards the receiver, and receiving antenna is expected to collect maximum signal power from space. So, an ideal transmitting antenna is one which pushes all its input towards the receiving antenna, and an ideal receiving antenna is one which is capable of collecting a maximum possible signal power from space. In transmitter, what exactly happens? Power and frequency of signal are upgraded. In receiver, power of signal is upgraded, but frequency is downgraded. Here it is, but. Transmitter and receiver antennas must be matched both frequency wise and also polarization wise. If transmitting antenna is emitting a frequency F, then receiving antenna must be designed so that it becomes capable of receiving that frequency F. It is called frequency match. Similarly, polarization match is also essential. If transmitting antenna is emitting horizontally polarized wave, then receiving antenna also must be polarized to receive that wave, horizontally polarized wave. It is called polarization match. Distance between transmitting and receiving antenna should be small enough signal is detectable by receiving antenna. When signal is emitted by transmitting antenna, it starts traveling towards the receiving antenna. While traveling, the strength of the signal that is moving towards receiving antenna, it keep on decreasing. If distance between the antennas is very large, then the signal strength at the receiving antenna, it may not be sufficiently large to be able to be detected by the receiving antenna. So distance should not be too large. This slide basically gives information pertaining to wireless communication systems and the importance of antennas in the overall structure of wireless systems. Here are given some information regarding IEEE radio frequency bands. Wireless and radio, these are synonyms. In wireless communication systems, information is passed, transmitted from transmitting antenna to receiving antenna over a frequency. This frequency is called operating frequency, or center frequency. Low frequencies are not used because low frequencies demand larger dimensions for antennas. So, usually high frequencies are used. IEEE gave certain labels to frequencies that are used for wireless purpose. They are called IEEE radio frequency bands. We frequently use these labels, these names while discussing, while studying, while understanding wireless systems and antennas. Let us go through these labels. VLF stands for very low frequency. VLF band means it is range of electromagnetic wave frequencies from 3 to 30 kilohertz. ELF means low frequency. Its range is 30 to 300 kilohertz. MF means medium frequency. Its range is zero point 0.3 to 3 megahertz. HF means high frequency. Its range is 3 to 30 megahertz. VHF means very high frequency. Its range is 30 to 300 megahertz. UHF, its expansion is ultra high frequency band. Its range is zero point 0.3 to 3 gigahertz. SHF stands for super high frequency. Its range is 3 to 30 gigahertz. EHF stands for extra high frequency band. Its range is from 30 to 300 gigahertz. It is quite useful to keep this band's designation in mind while studying wireless communication systems or parts of wireless systems like antennas. Another band designation is also there. This is also given by IEEE. This is called IEEE radar band designation. Earlier one is radio frequency designation, whereas this one is radar band designation. Both are from IEEE. Radar is a communication system, wireless communication system. Earlier it was mainly confined to defense, but nowadays plenty of civilian applications also come into being for radar systems. Under radar band designations, we have certain labeling for frequencies. We consider them. Now HF means high frequency. Frequency range is 3 to 30. Wavelength range is 100 to 10 meters. VHF stands for very high frequency. Frequency range is 30 to 300 megahertz. Wavelength range is 10 to 1 meter. UHF stands for ultra high frequency. Frequency range is 0.3 to 1 megahertz. Wavelength range is 100 to 30 cm. L band is there. Its frequency range is 1 to 2 megahertz. Wavelength range is 30 to 15 cm. There is an S band. Its frequency range is 2 megahertz to 4 megahertz. Wavelength range is 15 to 7.5 cm. Then there is a C band. Its frequency range is 4 megahertz to 8 megahertz. Wavelength range is 7.5 to 3.75 cm. X band follows C band. Its frequency range is 8 to 12 megahertz. Wavelength range is 3.75 to 2.5 cm. Ku band is there. Its frequency range is 12 to 18 megahertz. Wavelength is 2.5 to 1.67 cm. Then K band, its frequency range is 18 to 26 megahertz. Wavelength range is 1.67 to 1.0 cm. Ka band follows K band. Its frequency range is 26 to 40 megahertz. Wavelength range is 10 to 7.5 mm. After that, millimeter waves are there. Its frequency range is 40 to 300 megahertz and wavelength range is 7.5 to 1 mm. Sub-millimeter waves, this band is also there. Their frequencies are more than 300 megahertz. Wavelength is less than 0.1 cm. Before going further, it requires to be mentioned that the naming of the bands L, S, C, X, Ku, K, Ka, it is done by defense establishment, US defense establishment, to maintain confidentiality. The naming is done in an haphazard, unpredictable manner, except that there is no other reason and there is no other importance also for the labeling in that manner. Here are given frequency bands and wavelengths of visible range. Visible range refers to frequencies that are sensible to human eye. Now, near ultraviolet, its frequency is 1 into 10 power 3 terahertz. Wavelength is 300 nanometers. Shortest visible blue, its frequency is 7.5 into 10 power 2. Wavelength is 400 nanometers. Blue color light, frequency is 6.5 into 10 power 2, 10 square. Wavelength is 460 nanometers. Green color wave or light, its frequency is 5.6 into 10 square terahertz. Wavelength is in nanometers 540. When it comes to yellow color light, frequency is 5.1 into 110 square. Wavelength is 590 nanometers. When it comes to orange light, frequency is 4.9 into 10 square. Wavelength is 610 nanometers. Longest visible red light, frequency is 3.9 into 10 square. Wavelength is 760 nanometers. Near infrared light, frequency is 3 into 10 square. Wavelength is 1000 nanometers. When we are in wireless systems, the information that has been provided in this slide and in the previous two slides, that information, it is required to be in our minds for proper understanding of the theory of wireless systems or antennas. Now we consider definition of antenna. Antenna or aerial. Another name for antenna is aerial. A definition has been given by IEEE. It is a means for radiating and receiving radio waves. This is a definition from IEEE. Antenna has two modes of operation: transmitting mode, receiving mode. It acts in transmitting mode when connected to a transmitter. In this mode, it is basically a radiator, generating or manipulating the radiation. When connected to receiver, it is in receiving mode, and in this mode, it is a probe collecting the signal from space. Antenna serves certain functions. Basic functions are listed here. Almost all the antennas are passive and linear. Active and nonlinear antennas do exist, but here the discussion is not about them. The basic functions of antennas are: one, to act as a transitional structure, converting guided wave into free space TEM wave and vice versa. And second one is to act as impedance transforming device. Transitional structure is one function. Impedance transforming device is another function. By matching the line and free space, avoiding reflections over the line. And the third function is to act as transmitting antenna is to direct the energy into the desired directions and suppress the radiation in the unwanted directions. And as receiving antenna, sensitive towards the desired directions, insensitive towards the undesired direction. What it says is, consider transmitting antenna. Here, input is coming to the antenna from the transmitter, and antenna then emits the wave into space. This is space. So input is from coaxial line, output is into space. These two are different media. Coaxial line, space are different media. So wave here is undergoing a transition. Not only that, here it is undergoing impedance transformation too. The impedance level of free space need not be same as the impedance level of coaxial line. So impedance change is also happening. Same is the case with in case of receiving antenna too. This pertains to first 2 points. Last point is the transmitting antenna requires to direct all its input towards receiving antenna, preferably sending nil in other directions. Similarly, receiving antenna requires to be sensitive. It must receive only the signal that is coming from the transmitting antenna and accepting no signal coming from any other direction. That point is being stressed in the last para. The region surrounding a transmitting antenna, it is separated in 3 parts. We use these 3 parts several times in the study of antennas, so they are being given here. It is with respect to a transmitting antenna, the region separation is defined. As already mentioned, an antenna can be working as transmitting antenna, it can be working as receiving antenna too. Region separation is defined with respect to an antenna that is working as a transmitting antenna. When D is the largest dimension of the antenna, then there is something called near field region, then Fresnel region, then Fraunhofer region. Near field region is nearest and it is reactive. Here energy rotation takes place. It is rotation, not going away. Fraunhofer region is farthest and it is radiative. First one is reactive, last one is radiative. In this region, energy movement takes place. Energy goes away. It is called radiation. In the first region, it is simply rotation, no going away. In between, there is Fresnel region. A definition is their mathematical definition. R less than 0.62 square root of d cube by lambda. R means radius. It is illustrated in the next slide. D means dimension. Lambda is wavelength of the wave. Fresnel region is in between 0.62 square root of d cube by lambda, 2d square by lambda. In between these two, Fresnel region. Fraunhofer region is r more than or equal to 2d square by lambda. Here is shown illustrated region separation. R1, R2, R3. R1 limits reactive near field region. R2 limits Fresnel region. Fresnel region is in between R1 and R2. Beyond R2, it is far field or Fraunhofer region. These expressions, they are already discussed. A few points now regarding radiation. What is radiation? Electromagnetic wave, traveling wave, going out into space is called radiation. Antenna is a device which radiates. Antenna and radiation are inseparable. Antenna is a hardware, radiation is software, connected, closely related. So we consider some points regarding radiation. Two basic features of radiation are: one, it is an EM phenomena in which the energy travels away from the source after getting detached from it. It is specific to and an important property of dynamic fields. Static fields cannot radiate, only time varying fields can radiate. This is the point. Static fields cannot radiate because they have inverse distance square relation. Anyway, point is only time varying electromagnetic fields have the capability to radiate. Two, only time varying currents or accelerating charges can radiate. Charge moving with constant velocity in a curved or bent wire or in a wire which is truncated or terminated can also radiate. As in all these cases, charge undergoes acceleration, deceleration. Certain terminology got developed around radiation and radiators. Radiators are devices which can give out radiation. Types of radiators, several types of radiators are used. While studying antenna theory, we come across certain radiators. They are basically three types: isotropic radiator, directional radiator, omnidirectional radiator. What is isotropic radiator? It is a hypothetical non-existent radiator. It doesn't exist in reality. For study purpose, it is used. It is useful. Theoretically, it is important. As already mentioned, it doesn't exist, but for understanding performance of different radiators, comparison purpose, isotropic radiator is useful. Directional radiator is a practical and real one. All real world antennas belong to this category. Directional radiators. Omnidirectional radiator. It is directional except in one plane. Example is broadcasting antennas. So what is isotropic radiator In brief, let us suppose, imagine a spherical shaped solid radiator like sun, sun, sun. Sun radiates more or less equally in all directions. Similarly, if a radiator radiates, sends out equally in all directions, then it is called isotropic radiator. What is directional radiator? In reality, isotropic radiators do not exist. Real world radiators, they radiate more in some directions, less in some other directions. So their radiation exhibits certain directional nature. Hence, they are called directional radiators. What are omnidirectional radiator? It radiates more in some directions. It radiates less in some other directions. But in one particular plane, it radiates equally well in all directions. In such case, it is omnidirectional radiator. Here is given a definition. Isotropic radiator is defined as a hypothetical lossless antenna having equal radiation in all directions. Although ideal and not physically realizable, it is often taken as a reference for expressing the directive properties of actual antennas. For this radiator, radiation field is independent of direction, theta phi, and E max is constant for a fixed R. Here one point is required to be mentioned while studying antenna theory. In the analysis of antennas, in providing specifications of antennas, spherical coordinate system is used, not rectangular, not cylindrical. It is the spherical. Coordinates of this system are r, radial coordinate theta, polar coordinate phi, azimuthal coordinate. Direction is specified by theta and phi in spherical coordinate system. Distance is by r. Isotropic means radiation is independent of direction, means independent of theta and phi. It depends only on distance. When distance is fixed, radiation naturally is constant. Now, some information regarding directional antenna. Directional antenna is the one having the property of radiating or receiving electromagnetic waves more effectively in some directions than in other directions. Omnidirectional radiator is defined as the one having an essentially non-directional pattern in a given plane and a directional pattern in any orthogonal plane. These are academic definitions of directional antenna, omnidirectional antenna. Notice radiator can be used synonymously as an antenna, but in industry it is the antenna that is used, but there is not much difference between radiator and an antenna. An omnidirectional pattern can be noticed as a special type of directional pattern. Regarding patterns, we are going to discuss clearly, deeply in the coming sessions. Now, power flow in radiation. As already mentioned, radiation refers to a traveling wave, electromagnetic traveling wave. Traveling wave is always associated with the power flow. So radiation is associated with a certain amount of power flow. Here we consider certain aspects regarding power flow. Quantities widely used to denote the power flow are the radiation intensity, the radiation density. Both give information regarding amount of power that is flowing in the radiation. A few points regarding radiation intensity. Units are watts per steradian. Radiation intensity is independent of distance. It is used in antenna theory widely. Whereas the radiation density, it has units of watts per square meter. It is a distance dependent. Basically, it is Poynting vector, E cross H. It is widely used in EM theory, electromagnetic theory. Some more information regarding intensity and density. Radiation intensity in a given direction is radiated power per unit solid angle in that direction. It is independent of the radial distance r and is indicated by u, function of theta and phi. Radiation density is also called power density. Radiation density, power density, these are synonyms indicated by S of theta and phi. On the other hand, radiation density depends upon the radial distance r and is by definition the power radiated per square meter normal to power flow. Before going further, it is to be mentioned here that it is the radiation intensity that is widely used in antenna theory. Normalization. What is normalization? If the maximum value of the field intensity, radiation density, or radiation intensity is set to 1, then they are called normalized field intensity, normalized radiation density, normalized radiation intensity respectively. So normalization means setting maximum value to 1. We come across normalization in transmission line theory also, but there normalization means referring impedances relative to characteristic impedance of the line, but here it is different. In antenna theory, normalization means setting maximum value to 1. Here is given density versus intensity comparison. Both refer to power flow. Power density is E square by eta. Units are watts per meter square. Eta is intrinsic impedance of the medium. It is 120 pi. If the medium is free space, E is field intensity. Radiation intensity is R square E square by eta. R is distance, radial distance. These two are related. That relation is U is R square S. Intensity is R square times density. With this, we come to an end of this session. In this session, the focus is on importance of antennas in the functioning of wireless communication systems, various frequency bands that are used for wireless communication purposes, different types of radiators, and a few important points regarding radiation, radiation intensity, radiation density, and their connection to field intensity. Hope this session is useful to you. We meet again in another session with a new topic soon.